So good morning. So now we are going to talk about the last topic. This is the last lecture, and yeah. So let me talk about. We are going to do some geometry today. So today is Geometry Day. Chapter 2, we are going to do convex, discrete maximization. So I'm going to give just an outline of the main result there. There are other variations, and you can see this in the book. So we are going to now maximize a convex function over integer points. And now I'm calling this discrete. I'm going back to the more general setup of discrete maximization. So S is not necessarily now coming from an integer program. It is just a finite set of Zn. Possibly, we will see later, possibly coming again as a set of integer points in a program, or a 0-1 set coming from some combinatorial optimization problem, spanning trees, matrices. We'll talk about that, going back to the introduction. And f is a convex function. So f is a convex function, let's say on Rn, for the time being, convex. And we want to maximize this. So let me give you start with a one-dimensional picture. So in one dimension, so this is n equals 1, dimension 1. This is the function. This is x. And suppose our set of points, so we have integer points. It's a finite set, so it must be some, suppose it's closed inside. That's not so important. But suppose this is the set S. It may have some holes, actually. Let's make some holes here also. So maybe it looks something like this. Some holes. So suppose this is my set S. This is S. Can you see these dots? These are integer numbers. And some lower bound here, some upper bound, and the set is really in this interval, possibly with some holes. And now the function, it looks something like this, maybe. It's a convex function. Just one tip, to remember to distinguish between convex and concave. So convex is a smile. I don't know. Convex is happy. So we stay with convex, and we either maximize or minimize them instead of dealing with concave functions. So this is convex. Okay, so where is going to be the maximum? And we are going to maximize. So there's a completely different story if we minimize. We've done that in the previous talks over integer programs. So minimizing convex function is nice in the sense that you have a unique global minimum, and therefore you can somehow iteratively go and look for this minimum. And continuous optimization, continuous minimization of convex functions is usually can be done quite efficiently. You can approximate this by some iterative algorithms and so on. But the problem is that the minimum, well, maybe I'll draw it a little bit like this. The minimum usually is not an integer point, so usually minimizing convex function is hard. But maximizing convex function is also hard, but it's a different story. And where will the maximum be? One of the endpoints, right? So it's going to be one of the vertices of the convex hull of S. So this interval here, this line, this interval is the convex hull of S. It's a polytope, one-dimensional polytope. And the maximization of a convex function is always, the maximum is always going to be attained at one of the vertices. So in this example, this one is higher. No, this one is higher. Again, it's not a good picture. Maybe this one is strictly higher than the other one. You see, so this is the maximum. This is the optimal solution. So it's a vertex. Now let's look on a two-dimensional picture. So suppose now this is dimension n. Let's look on dimension 2, two-dimensional picture. So So suppose my convex hull looks something like this. This may be the convex hull of S in R2. And again, there are many integer points inside. You see, I mean, there are many integer points, possibly some holes, some are missing. It's not so. But the convex hull of S will have, its vertices will have points from S. And now the convex function, so how does a convex function look over a two-dimensional polygon? So think about this polygon as lying horizontally on the table here, let's say. Then the function is something like this, like a bowel, right? And again, the minimum is going to be in the interior somewhere, usually not in an integer point, so it's a harder problem, usually. And the maximum is going to be attained where? So not only on the boundary, but there is always going to be an optimal vertex. So not just the boundary, but at the vertex. So there will be always some optimal vertex. And so, actually, when you know the optimal vertex, you've solved the problem. So the problem really is, in a sense, equivalent to, or reduces to, enumerating all the vertices. Now, let me say that the function, I want the function to be presented by an oracle. So I want the function f. The function f is given by evaluation oracle. So do you remember what an evaluation oracle is? You give it a vector, and it tells you the value of the function. That's the answer. And so it's given by the evaluation oracle. We cannot really see the function. We can just see locally on the point we ask. But on the side, we know we have some guarantee that it is convex. So we trust that. If it's not convex, our algorithm is not going to work. But if it is convex, and we have access to an evaluation oracle, we are going to be able to solve the problems. And now my question is the following. So look on such an S. Can you give immediately a lower bound on the number of queries I have to make to the oracle, which actually is the running time? How many queries do I have to make to the oracle at least to be able to solve the problem correctly? So let's look on this picture here. Actually in general, but okay, I got the answer somewhere. The number of vertices. And the point is the following. If you look on the vertices and I assign you tell me you assign whatever values you want to the vertices, since these are vertices, so if you have points which are convexly independent, you can always extend it to some function which is convex, and on the vertices you get exactly the values you assigned. And this means that now if you ask the oracle question on points of your set or other points, and let's say you ask the oracle on all points but this one, but one of them, it may be that the function, actually the best value is only there. And so you missed it, and so you cannot solve the problem correctly, unless you really ask the oracle on each vertex. Now this tells you immediately that even, so in general, you cannot solve such problems in polynomial time. You actually need exponential time. So here is an example, a very simple example. If you take S to be the set, it's a 0, 1 problem, simply all 0, 1 vectors, then you need 2 to the n oracle queries. So exponential time. So this problem is not I mean, the hardness of this problem does not depend on some computational complexity assumption like p does not equal np or something like that. Although anyway, does not fit directly because you're using oracle. But actually, you need exponential time. There's no way you can solve it in polynomial time. Because you need to ask, I mean, each one of those is a vertex, of course. That's something that you need to think about a little bit. So no 0, 1 vector is expressible as a convex combination of others. And the picture actually is the cube, you know. This is the convex hull of S. There's exactly 2 to the n vertices. Every 0, 1 vector is a vertex of the cube. So well, we are in trouble. So we have to restrict the class of convex function. And when we talked about minimization of functions over integer program, we also restricted it to be separable convex. So here we are going to have a different kind of restriction. Yes?
I was just curious. You said that you can assign numbers to the vertices and then come up with. You have like polynomials of bounded degree.
No. So yeah. So if you, that's that's of course a good question. If you have some additional structure on the function, then you may be able to exploit it and do something better. And that, of course, that's a good question, a good direction to study. And so what I'm doing here, I'm looking on the most abstract and general setup where I just have an evaluation oracle. So the function can be arbitrary. I have no formulas, no assumption of structure except for convexity. If you make extra assumptions, this is a convex polynomial of bounded degree, you may find a better way, and this is a nice problem. Yes? You also had a question? No. Yeah. Behind you. So we are going to restrict it, and now we are going to restrict it in a different way. So I think we don't need this. And I want to restrict it in a way which is still useful, much more general than linear. So we are going to look on the following restriction. So restrict attention to the following setup. I'm going to maximize a convex function still, but it has this composite form. And now W, this new ingredient here, is a d by n matrix, and we may assume this is integer. Again, if we scale it, if it's rational, that's not a problem. If it's real, we are in some sort of problem. We want to work with rational data. So this is an integer d by n matrix. And so the idea, you see, we take every n-dimensional point, so and multiply by the matrix, we get a d-dimensional vector. We project down to d-dimensional space, and then we apply a convex function on Rd. So f is a function on Rd now, convex, evaluation oracle. This is the matrix. It's encoded nicely in the binary encoded naturally in binary. I mean, the size is going to be this. What else? And S, I didn't tell you how S is presented. So S, how is the set presented? Because now it's not an integer programming. I'm talking about a more general set of, so I have to tell you how it is presented. And the presentation is going to be by a linear optimization oracle. So we assume we can do linear optimization. This is our starting point. We can do linear optimization over the set. And we want to use this and solve harder problems of maximizing convex function. So this is given by linear optimization oracle. And this means if you ask this oracle on some linear function given by some vector little w, different than this big W, given by that queried on this, answers some point, let's denote it x sub little w in S, which solves the linear maximization problem over S. So is this clear? Maybe I should take this board up. And this down. And I'm going to use this board a little bit more. maybe actually I want to no, I just erase this. So is this linear optimization oracle clear? I mean, do you see what I mean by this? And this makes sense. I can solve linear optimization, then I want to do more. So there are lots of examples where people know how to solve linear optimization, trees, for example, matroids. And
is S always the integer ones that you do the linear optimization over, or is S like the convex hull of those things?
S is the integer point. S is a set of integer points, a finite set, and its convex hull is going to play a role here. Right, so actually this is equivalent sort of, yeah, I mean, because linear are convex, so again, you're always going to get a vertex, which is, if you optimize over the convex hull, again, you're going to get a vertex. You can get a vertex. So this is given by a linear optimization oracle, so it gives you, for every integer vector, it gives you an optimal solution in the set, which maximizes this linear function. And I should actually tell you also that the W here, this matrix, you can regard it as, the rows give you D linear functions, which you can regard as different criteria, D criteria, and then this F sort of balances them and gives you value, this kind of common trade-off between these criteria. So this is the interpretation here. And of course, this is more general than linear, because if you just take one row here, dimension 1, and F is the identity, you get, again, a linear function. Okay, so the picture is now the following. So this is Rn, and this is the picture. Is this board clean enough to see this? Maybe I should actually do this nice picture over on some clean black board. This one. Good? It's running out of chocolate. What? This one, yeah, I'm using some pieces. I still have enough. It's not so. Okay, so here's the picture which we are going to use throughout the rest of the lecture now, actually. So here is Rn. Our original set lies somewhere here. It's a large set of discrete points. I don't know. Maybe there's some hole and so on, but anyway, it's a big, complicated set. And I take the convex hull. So, well, I'm not sure I can draw such nice pictures here. Maybe, I don't know. Does this look three-dimensional? Not so much. It's supposed to be three-dimensional. I have better pictures in the book, I don't know. So, well, that's not so good. This is supposed to be a three-dimensional picture.
You erased integer points.
Yeah, so forget the integer point. This is now the convex hull. Oh, this is bad. This is not a good picture. Let me. Maybe just do a little bit simpler and it will be more. Yeah, I think this is better. Okay, this looks better. This will look more like three-dimensional thing, maybe. Yeah. So the points, this is the convex hull of S. S has more points, but in particular, since this is the convex hull of S, all vertices are in S. S is a finite set in Zn. This is Rn. And now we take our matrix. Thanks. Meanwhile, oh, wow. Good, we can go for another week then. So now we project down using this matrix W to Rd. And now we really want, so you see it's just below this, and we are going to get some polygon. I don't know, something like this. Well, I mean, of course, in general, the one below is going to be simpler than this one. Maybe this is not the case in this figure. But it looks like this. Again, there are some integer points inside, some holes. But when we do convex maximization, we don't really care about the holes. So actually, I should say in the book, there's a chapter 6 which deals with arbitrary nonlinear optimization over combinatorial systems. And then we actually have to look on the holes also. It's more complicated, and then the W has to have small entries, unary entries, and we can do some things. But here we are doing convex maximization. And now comes the function. So the function, there's above this sits this surface. Right? Above this d-dimensional thing sits some surface of the graph of the convex function. But let me just simplify it and write something simplistic like this again. This is supposed to represent the value of the function somehow. And so this is a little bit cheating, this picture, but I think you get the picture. So the maximum here is going to be, so where's the maximum over this? So this should be some surface, really. So the maximum may be somewhere here. Right? And then the optimal solution is not here. It's somebody in S, so it should be some pre-image of this guy. Maybe there are many, so maybe this is one of those guys that projects down to this. So this is the procedure. So basically what we need to do in view of what I explained before, we have to actually construct all the vertices, ask the oracle of F on each one of those vertices, and then find some element in the fiber of some of these, one of these optimal vertices. So the fiber means one of these elements in the original space, Rn, which are in the set S, which project down to the optimal vertex here. This is the procedure. But the problem is how to do it computationally efficiently. So this is the question. And you see the problem, these pictures are only in our mind for the time being. Because we cannot compute this. I mean, even this, the convex hull. You see, all these pictures are just abstract in our mind because the oracle S is given by an oracle. We don't have an explicit list of this element, which you can just access oracle. And we don't have, definitely we don't have explicit access to this projection here. And even F, we can just ask on points. So it's not so clear algorithmically how to do that. And indeed, it's not going to work in general. So in general, if you just take an arbitrary set, even just a set of all 0, 1 vectors, the cube that I had before, and you project down to fixed dimension, even dimension 2, it may happen that, depending on W, it may happen that all the points become vertices. You still may get 2 to the n vertices on this polygon. So you can definitely make exponentially many vertices even down there. And then again, we have the same argument. Using the oracle, you must ask on every vertex, even if the dimension is fixed. We have to have some more assumptions on this, on the structure of the set. So I'll soon define this, but let me see. I wanted to say something more before I proceed with this. Yeah, I know what I wanted to say. So let me just tell you, what can we do with this linear optimization oracle of S, for example? Suppose, so keep this picture. We're going to use it later and extend it a little bit. But suppose, let's look again on the situation of dimension 1. So this is my S. And this is the convex hull of S, and this is a real line somehow. And now I have this convex function, and I know the optimum is going to be, let's say, here. And I want to find the vertices. How can I use a linear optimization oracle over S to find the vertices? So here's the question. Can we use the linear optimization oracle of S to find the vertices of the convex hull of S? In this specific, in dimension 1. Dimension 1, how do we do that? Yeah, I mean, and mean. So I got the answer. You have to compute the maximum and the minimum, which means formally I would just take two linear functions. I would first take this W to be the unit vector, 1, 1. I don't know this, but the unit vector, and I maximize this, right? Maximize 1, 1 over S. Then this gives me this vertex here, this V plus, let's call it, in S. And then I take W to be minus 1, 1. So and I maximize this, I simply want to stay formal with the oracle the way I put it. We are maximizing an objective function. So then we maximize, again, minus 1s, or minimizing this, and then we are going to get the other vertex. There are always going to be two vertices only, v minus. So this is easy, right? But using the linear optimization oracle, you can do something. And in the higher dimensional situation, so suppose I have a linear optimization oracle here. So look on this vertex, for example, this guy here. Well, it has a cone, the orthogonal cone. This is called the normal cone. It's actually quite, well, it's not the tangent cone that Matthias was using, but it's sort of, you already have some feeling for this cone. The normal cone of the convex hull of S at V. This is V. Let me call the convex hull of S P, and let me call the projection. So let me call this down here Q. So Q is the convex hull of the projection, which is W times S. And if I have a vertex, I have this normal cone. So what is the normal cone? So do you know what the normal cone is? So the normal cone consists, I'm thinking about this as a homogeneous cone. So actually you translate it to the origin. And then every vector in this direction, if you use this as your W for the linear optimization oracle, the optimal solution is going to be at that vertex. And actually you want to think about the open cone. So the relatively open cone, whenever you take a vector in the relatively open cone of a vertex, the unique maximum over the polytope under this vector is going to be at that vertex. And every vertex has such a cone. Just take a, so there are other cones here, you see, and they tile nicely the space. So you have these cones. And also higher dimensional faces. So in this picture, this facet, how is going to be the cone of this edge here? How is it going to look? Just one vector, the orthogonal, this one. Right? So this vector, if you maximize this vector over the polytope, then the maximizers are exactly those which lie on this face. We have a nice collection of cones. This is called the normal fan of the polytope, and they tie nicely the space. And whenever you take a vector on one of these open cones and you maximize it over the polytope, the set of maximizers is going to be exactly all the points on the corresponding face. But we are really interested in vertices and these full dimensional or maximal dimensional cones. Yeah, you had the question.
Wondering, is this normal cone the interior of the polar cone of the tangent cone?
Yeah, the interior of the polar. Yes, yes. Yes. So, okay. So this is the picture. Okay, so now I'm kind of hinted you what we want to do, right? We want to somehow dig all these vertices. And you see, the way is somehow to find vectors in these cones and somehow maximize these linear functions and get the vertices. But to maximize, you cannot maximize here. We can maximize over S because we have an oracle up in Rn. So this is roughly what is going to happen here. And so let me move on with this. We're going to come back to this picture later. Now I need to make some definitions. So we need some tools here. So we need some tools and some restrictions on the set S, and then in the end we'll see some example where it works. So, okay. So let me define a zonotope. What is a zonotope? Definition. A zonotope, okay, let E be a set of vectors in Rn, or Dn, let's say D, in Rd, a finite set of vectors. Then the zonotope generated by E the zonotope generated by E is, so Z, the zonotope of E. I mean, you know the definition of a polytope. The convex hull of points, you know, right? You've seen this last week. But the zonotope is a certain polytope which is defined. There are several ways to define it. Let me use the 0-1 version. It's nicer to draw pictures. So it's the convex hull. Well, there are various ways to define it. Let me use the convex hull. So the convex hull of maybe I'll give two definitions. So the definition is a set of all vectors of the form some combination of the EI where each lambda is between 0 and 1. So you take non-negative real combinations of the vectors, but now each lambda is between 0 and 1. And this is the convex hull of those where you take exactly 0 or 1. So the convex hull of the partial sums here, let me write this, EI, I in I, such that in 1, 2, m. Yes. And let me make a picture of one of those guys. And this will explain the thing. So let's look on some example here. So let's look on these three vectors in R2. Forget this thing for the time being. This will show up later. This is just for me. Footnote for myself. And so again, I mean, you may wonder what this is going to be. But let's look on these vectors, for example, in R3. So forget this definition here. Let's look on this constructed. This gives you a simple way of constructing a polytope. You look on all 2 to the m subsets, sums of vectors, and you take the convex hull, right? I mean, is this clear, this expression? I take all possible 2 to the m subsets of the generating vectors. I form the sum. I get 2 to the m vectors, take the convex hull. In particular, if I take the empty sum, then this is 0. So 0 is always there, okay? And so let's do this zonotope. The way to construct it more nicely, you can do it iteratively. So I take E2 and copy it over E1, and I form this parallelogram. So this guy here is the zonotope generated by E1 and E2 only. And now to add E3, I take the same thing and copy it as it is over here at the end of, let's see, so like this, like that, and like that. And then I take the convex hull of the whole thing. So this is it. No, I took it and I simply had to edit by taking, so this piece is obtained by taking 0 coefficient on the E3. And then I take 1 coefficient on the E3, so I get E3 plus the entire thing here. And then I take the convex hull. So this is it. And you see there are parallel edges. This is parallel to this. This is parallel to this. This is parallel to this. What?
E1 plus E3? That should be almost E2.
E1 plus E3. Yeah, well, but it's, I mean, this is a zonotope. No? I made a mistake. Anybody wants to come and draw it? No, really, what's the problem then? E1, E2.
I mean, shouldn't this one, you have this one here?
Yeah.
E1 plus E3.
Go ahead, yeah.
So it's
Yeah, I mean, maybe I'm not doing it nicely.
this one, and this one,
Mm-hmm.
and then this one. E1 plus E3. And like this, right?
Yeah.
Two parallelograms, and one is translated with
Yeah.
E3.
So that's a better picture. We'll take your picture, okay? Thanks. No, yeah, definitely better.
Sorry.
Definitely looks nicer, I mean. So, okay, so we take this picture, thanks. Let's take, anyway, but now you understand how to do it. And so you see, I mean, when you draw these pictures, it's a little, if I give you more than 3, I give you 10 vectors, then it's going to be even harder to do it properly. And if you go to higher dimension, we can not draw pictures, right? So it's not so convenient to compute this. And the algorithm, this suggests an algorithm. What is the algorithm? What's the complexity of the algorithm suggested by this formula here? I construct 2 to the m sum and take the convex, so it's exponential, just to write them down. And then if I actually want to filter down the vertices, it's not so important, but suppose I actually want to clean it up and get the vertices, it's even more complex. So it's not so convenient, and this is, has nothing to do with the dimension, you see, because even in dimension 2, I mean, it depends on the number of generators. But it turns out, and I don't have time to explain this, there's a nice way to construct them, and you can think about actually inductively doing this like this. The point is if you have m plus 1 generators, first you construct the zonotope of m generators, and then one can show that many of the points are not vertices. So they kind of disappear inside. You have few vertices, and then you just take this, copy it again as we've done here, take the convex hull, and it's always going to collapse the number of vertices. So there's a theorem, and you can find, again, you can find it outlined in my book in chapter 2, that here's the theorem, that the number of vertices of a zonotope in RD generated by m vectors is, well, roughly, let me just say it's roughly m to the d minus 1. For d at least 3, let's say. If the dimension is 2, then I think it's m to the d, m squared, but otherwise it's m to the d minus 1. But the important thing is not 2 to the m. So among the 2 to the m subset sums here, most of them disappear, and you just get a polynomial number of fixed dimension, a polynomial number of vertices, and you can construct them in polynomial time. And so let me actually say, let's fix d, fix the dimension, then the number of vertices of a zonotope in RD is generated by m vectors is this, and the vertices each vertex v, and the vertices and representatives in the cone, I'll explain this, representatives in the normal cones can be constructed in poly time, can be computed in polynomial time. And polynomial time again means something like this, order m to the d. So what do I mean by representative at the cones? So here's the zonotope. And now again we have this picture of normal cones, open normal cones with vertices. This guy, this guy, this guy, this. And you see that actually if I copy them all to the origin, I get just a nice partition of the space. This is a so-called normal fan of this polytope. So, well, again, the picture is not so good. Something like this, and this, I think, and yeah. It's a nice fan. And so I can compute in polynomial time the vertices and a representative in each outer cone here, in each normal cone. This can all be done. So for every vertex v, I'm going to have some hv here. So what does this have to do with our optimization problem? Well, here comes another lemma. This is bad. This is the same polytope exactly. That's good. Let me do another one. Let's look on this. So let's suppose this is a P, and here comes another useful lemma. And the lemma says the following. First I have to give you a definition. So here's another definition. An edge direction of a polytope is any non-zero vector parallel to some edge of the polytope. Some edge of the polytope. So edge means a one-dimensional face. And here is another lemma. Let P be a polytope. B a polytope. And let E be a finite set containing all edge directions. Well, a direction for each edge. And the direction of each edge. And then the zonotope generated by this set is a refinement, and I'll explain this, of P. So, okay, so so let me explain this on this picture. So what is an edge direction? Here is a polytope. So what are the edge directions here? Let me draw them. This is the origin now. What are the edge directions here? Well, the horizontal one. So there are two parallel edges here. And so if I choose any non-zero vector in this direction, let's say, as my E1, this is an edge direction that covers these edges. And then I have for this one, another one like this, right? Let's call this E2. And then this guy gets another edge, E3. So I have the polytope, I have polytopes, I have the edge directions. And now the lemma tells us that if we construct the zonotope generated by this, which is this nice picture, then this is a refinement of this. And refinement means now that you see the cones, the normal cones, refine the cones over there. So if I look on the cones here, the cones of this guy, then actually the closure of any cone here is the union of some closure, of the closure of some cones here. So for example, this guy, how do you get it from this guy? Yeah, it's just one, right? This one is exactly this one. This one, how do you get this guy? This one is the union of these two. You can actually maybe look here, maybe that's better. So the union of these two is this one. You see, and so on. And this guy here is the union of these two, and the one up there is again this one. So now so the idea is going to be the following. Somehow we construct these, and then we take the representative, these h's, and I pick them here. So here is one h. Here I get two h's, one from this cone, one from this cone. Here I get one, and here I may be getting two from the zonotope. And so now let's complete the algorithm, and then we'll do some applications. So I mean, this is really a little bit of a rough outline, but I think we have enough information to explain the algorithm now. And the theorem, I should tell you what the theorem is. So maybe I should first say what the theorem is now, and then we'll outline roughly the algorithm and give two examples of this. So that's the plan. This is the main theorem of this chapter, but there are other variations there. So here is the theorem. Theorem, let me do it again formally. For every fixed dimension, fixed d, again, the dimension is just the number of linear criteria in the function. It's not the dimension of the set is variable, it's n. For every fixed d, there is an algorithm. That given a function from let's say zd to z convex, the evaluation oracle set finite or not finite doesn't matter, but set S in Zn given by a linear optimization oracle matrix W, let's say in Z d by n. So I'm talking about this optimization problem. And what else do we need here? And a set E of all edge directions of the convex hull. Solves the maximization problem in polynomial time. And again, I'm not going to tell exactly what the polynomial time is, roughly in the size of this set and in the binary encoding of this, in the natural input size. So we can, starting from linear optimization over S, we can do convex maximization. And the only really restriction here, well, the fact that this fix is okay, I mean, because as I showed earlier on, you quickly run into a situation where you have exponentially many vertices. But the real restriction is that we have to have a set as part of the input. We have to somehow know something about the set S and have a set of all edge direction of the convex hull. And I'm going to show you examples where this is actually natural and useful. But let me tell you how we prove this theorem. So here's the algorithm. We actually almost can do the algorithm now on the board. So here is the idea. So this is the proof now. Proof and algorithm. Okay, so what should we do here? So the idea is the following. Look, we have the set S, we have the convex hull, and now we have the set E of edge directions. This is also given. Edge direction of this guy, right? So just listen, see what, I'm going to outline this. We have the edge direction of this guy. Now we project this using W. So we just multiply each vector by W. We get a set of vectors in RD, like the one I like to draw over there, this guy here. Something like this, maybe more. Let's keep it the same picture here. We get this set in RD. Now we construct the zonotope. So we get something nice, symmetric, like this. We get the cones, and we get the vectors at the cones. We get many vertices and some HVs. And this is this zonotope of E. Zone WE. And now what we do is the following. So this is the entire idea. So you pick one of those guys at a time. We compute this in polynomial time using this lemma, computational geometry lemma here, that you can compute the zonotope in polynomial time in fixed dimension. Pick any vertex, pick the corresponding vector which you already obtained. And now you want to somehow use it to dig some vertex here. So how do you do it? You take this guy and you lift it up to some linear function here. So, and the way to do it is now so I don't need this now. This is here the convex hull of S. So now I take this HV and I do W transpose HV. Let's call this GV. This is an n-dimensional vector. I give you the recipe. I think you get the general idea. You need some proof here. You take this vector, multiply it by W transpose, you get an n-dimensional vector. Now you use this and ask the oracle of S to optimize this over the polytope. So you optimize, and it will give you some, this is the optimal solution maybe, and this is the optimal vertex here. Let's call it XV. The oracle gives you back this point, the oracle of S. And now you project this point back. Simply you multiply it and you form some YV to be the projection of this XV. This is this point, and this way you found this vertex. Maybe I took this one, I took this one maybe. So this was HV, and I found this vertex. And now I do this for all of those guys, one by one. And for each one of those I do, and then this way I get all the vertices in polynomial time. This is the algorithm. So I need to solve a linear optimization problem over S as many times as there are vertices of the zonotope. And the zonotope, actually, this guy usually will have much more vertices than this guy, because you see there are repetitions. This cone it comes from two cones. So this guy has more vertices, but it's more structured, so it's easier to control it. And so you do this, you go up to here, you get the vertices. Now you evaluate the function using the evaluation oracle or a comparison oracle. Pick the best, and now you just look up which is the guy that gave you this. So you already have some feasible solution there, and that's going to be optimal. Okay, so let me give you two applications. And this will conclude the lecture and the entire series. So here are two applications of this. And you see it's also a complex procedure because it involves m to the d vertices of the zonotope. So you have to solve m to the d linear optimization problem. So here's one example. Well, so let me start with this example, which we actually have been dealing with for about 4 lectures before, integer programming. So integer programming. So we want to maximize in this setup f of wx equals b as usual, and suppose we are given the Graver basis. Suppose g of a, the Graver basis, is available. And you know, you've seen examples, let's say n-fold systems, tables, universality, you have the Graver bases. Now, we can do the following thing. So what is our set S here? I'm going to be a little bit rough because I want to give another example. So what is the set S? Here, what is the set of feasible points? What? All the integer points, just without this, right? All the integer points satisfying these equations and the lower and upper bound. This is our S here. It's an integer programming setup. To apply this machinery to this optimization problem, F is convex, I should say, of course. F is convex. Well, I mean, the same setup is up there. To apply the machinery, I need, first of all, I need for S. What do I need for S? Linear optimization oracle. I need to be able to do linear optimization over S. Can I do linear optimization over S? Yes, because we have the Graver basis, and this was a theorem we proved before. So if we have the Graver basis, let's say in an n-fold system, we can do linear minimization over this, and this is non-trivial. We need the entire machinery of Graver bases. So we can use GA to realize or realize a linear optimization oracle for S. That's the first ingredient. Okay, so and the function is given by an evaluation oracle, that's not a problem. What's the other ingredient we need to apply this machinery? Edge directions of the convex hull of the integer points. So, and here comes a miracle. A set of edge directions of the convex hull. So actually this convex hull is complicated, very complicated object. It's called the integer hull. The convex hull of the integer points this object is so-called the integer hull. And it's usually very complicated to compute, but the set of edge direction of this guy, this is the convex hull of S, is what? Any guesses? No. The continuous relaxation is far away above this, usually. It's not totally unimodular. It's not going to be this. Yeah. This is a complicated object. The continuous relaxation will not help you here at all. The zonotope is the one I generate from the set of edge directions, but I need the set of edge direction to start with that corresponds to the set of feasible points S. Well, that's again too simple, too good to be true, and the answer was here. So the Graver basis happens to also be a set directions. Now this is the miracle. One can show this. It's not so complicated, so this is fantastic. I mean, it just fits right into this theory, and we can use it twice. So it's actually, the whole thing is quite complicated. You construct the Graver basis, let's say in polynomial time for n-fold program. This is now your E. So this becomes E. You take this guy, and now you apply the Zonotope construction. You need order m to the d minus 1. You'll get order m to the d minus 1 vector. What is m? The cardinality of the Graver basis, which may be very, very large. And this goes to the power of d minus 1. This is the number of vectors, vertices of the Zonotope. For each one of those, now you need to solve a linear integer programming problem using this iterative algorithm, using the Graver basis. So this is a horrendous algorithm, but it's polynomial time. And once you know it's polynomial time, there's hope that you can maybe get a better algorithm. It's there, you know, it's in P. So, and also this, because it's so complicated, it means that something very deep is going on, and so this is very good. So let me finish, if you allow me 5 more minutes, to go back to the original, the first lecture on combinatorial optimization, give you an example on spanning trees. So spanning trees and matrix, that's the last example, because this machinery applies also for not only for integer programming. So I want to conclude with this. Where will we do that? Maybe over here. Yeah.
Can you just clarify what you mean by, or how you can use the greater basis to realize the linear optimization?
Yeah, I'm saying that what is the linear optimization oracle? I just need to minimize linear objective functions repeatedly, different objective functions over this set. But minimizing over such a set with the greater basis is something we've seen in chapter 3. You remember this iterative algorithm, we keep augmenting, getting better and better solution by going along greater basis directions in polynomial time. So we need to do it repeatedly. The algorithm, the first algorithm from chapter 3. So there actually the algorithm for separable convex minimization, which in particular include linear. That's okay? So let's go, I'll keep this picture. So let me give you the final example here. So here is the combinatorial optimization example. Combinatorial convex maximization, let's call it. So let's look on spanning trees in a graph again. Let's say the graph is connected. So let me give you an example. Let's try to do a non-trivial example. So E1, E2, E3, E4, E5, 5 edges. And let's also give numbers to the vertices. So V1, V2, V3, V4. And now let me form the incidence matrix, but let me just choose an arbitrary orientation. So choose an arbitrary orientation. Let's say this. Doesn't matter. And we form now the incidence matrix of this graph. So we have 5 edges, 4 vertices. And actually, we can always erase one vertex because the rows are dependent here. So let me erase one vertex. And also, we don't need this guy. OK, let me first do. So let's draw the thing quickly. V1, you see it leaves. So minus here, plus here, 0. So I don't need I can always erase one row. Doesn't matter. And now let's do the second one. So E2 goes from V2 minus 1. V3 gets plus here. E3, what is E3? V3 minus 1. V4 is not here. And E4 minus here and 1 on here. 0, 0. E5 minus on V3 plus on V1. So is this clear? I mean, how I construct the matrix. And now look on subsets. So a subset of the index set of the columns. So this is the same as the edge set of the graph. A subset of this is linearly independent if and only if it's a spanning tree. So, yeah, so do you know this? I mean, have you seen this? Well, so again, now I identify the columns or the index set of the columns at the edges, and then the claim is that a subset of the columns is the columns are linearly independent if and only if this is a tree. I should say actually a tree. And a base is if and only if, let's stick to bases. Is a basis spans the column space, spans the column space of A if and only if it's a spanning tree. Okay, so a basis. If the graph is connected and I removed one row, the rank is going to be exactly the number of vertices minus 1. I mean, you know that the size of a spanning tree is the number of vertices minus 1. And now, so spanning trees becomes just bases of a matrix. And one can ask a more general question. Let's look on a matrix. It's a more general combinatorial optimization problem. Look on a matrix with n columns, and define your set of feasible points, the 0, 1 points, to be the 0, 1 vectors encoding subsets of the matrix which are bases of the matrix. And this is called the matroid. And in fact, there are matroids are even broader than that. But well, I'm getting. Oh, well, okay, 5 more minutes. Is this okay? We're done with that. 5 more minutes. It's a crash course on matroids. So, okay, so more generally, a matroid, more generally than spanning trees, let S be the set of indicators of bases of sum of any m by n matrix A over any field. Actually, it works for finite field also and everything, over any field. And there's more than that, so there are issues there. So your matrix can be over arbitrary field, and the linear independent structure comes from the field, and then you do. And this is now. So now I want to optimize over this. Then a set of edge directions of the convex hull of S is okay. A guess. A guess. Now we need 1 more minute. What's the set of edge direction of the convex hull of S for any matroid? This is very simple. The differences of 2 unit vectors, that's all. It's an exchange. If you see a matroid, there's this exchange axiom which defines a matroid, the set of all pairs of differences of distinct unit vectors. So you have n choose 2 of those. And the conclusion from this is we can now apply the theorem and maximize convex function over spanning trees and matroids. And if you remember in the introduction, this was the first example that I showed you. Convex maximization of some 2 by 6 matrix over spanning trees in a graph. You remember this first example. So the corollary can solve max fwx x bases of matroids in polytime. And this is f convex wd by n. So this is actually a much easier application than the Graver basis, but we talked mostly on integer programming. So here you see the set of edge direction is trivial. You write it once and for all. In the situation of integer programming, the set of edge direction is the Graver basis, which is a monstrous set. You have to compute it. And it's completely strange, but it does give you the edge direction. Okay, so this concludes my lectures here. Thank you for listening. I hope you got something out of it, and you will and maybe you'll be interested to pursue this research theory further. It's fairly new, the whole thing. Because I'm saying 2 or 3 years. There are many papers with many colleagues on this, and the monograph really gives a quick introduction to the whole thing. With really, you almost need no background, just mathematical maturity. Okay, thanks, and good luck in your studies. Later.